All right, so sequences. Actually, before sequences, there's one more. Have we done the equation solving part? No, right? I think we didn't. So let's have a new file. New file. And we're gonna start a file called bisect.py. All right. So first question we try to solve, first problem we try to solve is that of solving an arbitrary equation, right? Finding the roots of a function. So let's say we have a function f, right? That we don't know what it is. We want to make it possible to solve arbitrary equations with arbitrary functions f. And I'm interested in finding the root of that, right? So fx equals 0. What's the x? What's the value of x for which f of x is equals 0, right? So for instance, if I have something like x squared minus 3 equals 0, right? I would like to find a root being around the value of square root of 3. Now, how do we solve an equation like this? So if you think of the graph, right, of that function, when I say fx equals 0, the graph of that function has to intersect the OX axis somewhere, right? So what we want to do is specify the function f and some limits within which we want to search for a solution, right? So for instance, if we use x cubed minus 3 or x squared minus 3 equals 0, let's say I define the limits for the search, the range for the search to be between 0 and 100, right? So I'm guessing that somewhere between 0 and 100 there's a root. And indeed, if you look at the graph, right, f0, fx is x squared minus 3, right? So f0 is minus 3, and f100 is 100 squared minus 3, which is a very high, very large value, right? So on the left, I have a negative value for f. On the right, I have a positive value for f. We know that the function is continuous, so somewhere it must cross the OX axis, so there must be a root. Yes? How do I go about finding the root? Well, I don't want to find exactly the root. I want to find a good enough approximation, right? Because as you probably will find out later, the numbers inside computers are approximate anyway. There's no such thing as an infinite precision number. So, for instance, square root of 3 is a irrational number, and it has an infinite number of decimal places. This is something we can't represent inside a computer, right? So the only chance we have is to find some sort of an approximation. So we're going to use a method called the interval bisection method, right? We have an interval between 0 and 100, so we go to 50. And we say, f50, is it positive or negative? If it is positive, it means that the interval of interest can be reduced from 0 to 50. If it's negative, the interval of interest can be reduced to 50 to 100, right? So remember, f0 is negative, f100 is positive, yes? So if f50 is positive, it must be that the root is between 0 and 50. If f50 is negative, it means that the root is between 50 and 100. So having done this, we can continue. We can do the same thing. The middle between 0 and 50 is 25. What's the value of f25? Is it positive or negative? Right? So if it's a positive, I have reduced the interval to 0 to 25. Otherwise, I go to 25 to 50. Right? And by going with this decision process, I can narrow down the interval quite fast and quite precisely. When am I going to stop? When the width of my interval is very, very small. I will choose a precision, let's say 10 to the power minus 6. That's good enough for me, right? So whenever the limits 0 between left limit and right limit is smaller than 10 to the power of minus 6, I can stop. And the average between the two limits the limits of the range can be considered a good enough approximation for the solution to the equation, right? So this is something we want to do today. Before we go there, right? And you've played this game before, right? You've played this game where you have to guess a number between 1 and 100, right? I ask you to pick a number between 1 and 100, and then I'm gonna, in order to guess it, I'm gonna ask, is it greater than 50 or less than 50, right? So you're gonna say greater than 50. So suddenly my interval of interest is between 50 and 100. I have halved it, right? Then I'm gonna go to the middle of that. Is it greater than 75 or smaller than 75? And you might say, well, smaller than 75. So now I'm between 50 and 75. Is it greater than 67.5 or 67, right? Greater or smaller. So at some point I'm going to reduce the interval to 0, right? And I will find your number. How many steps do I need in order to do that? Approximately logarithm base 2 of 100, right? Which is, I can't remember, it's 5 or 6. Cool, all right. So before we go there, right, I said that we want to solve this for arbitrary functions, all right? So how do I define an arbitrary function? Well, it turns out that we have this expression called a lambda, right? So I can say lambda x times x minus 3. So this is fx equals x squared minus 3, right? I can define f to be this, and then I can apply f to, say, 10, and I'm going to get the result, 97, right? This is equivalent to saying def f x return x times x minus 3, right? It's exactly the same thing. However, right, and notice what I can do now, right? I can define a function g of h, right? And I can say return h applied to 5 plus 2, right? So if I am to invoke g now, what is a good argument to g? A function, right? So I can put f here, and I get 24. If I say g10, let's say, I'm going to get an error. Why? Because look what happens to h. H here is applied to 5, right? So if I say g10, I would get the expression 10 bracket 5, which doesn't make any sense. But if I say gf, then I'm going to get f applied to 5, and because f has already been defined, I can invoke f and get a result. Yes? So functions are objects like any other, right? We have already seen numbers as objects, right? We have seen aggregations of numbers, lists and tuples of numbers. Well, functions are also just objects. They can be defined, and once they have been defined, they can be passed as arguments. Yes? So this is how we are going to pass in an unknown function. We don't know upfront what function do we want to pass in. For instance, this expression will be just great for x squared minus 3, which is the function that we used in our example. Okay, so let's start by solving our equation, right? So our equation takes in a function f, and we want to solve fx equals 0, right? What is the value of x such that fx equals 0? And I'm going to have a low limit and a high limit. And notice how we define things, right? We write the name of the procedure we want to define, we write its arguments, and then we write colon, and then we can write the body of that. So let's see. Let's define above this a value called epsilon. And we make this 0.12345 and a 1. Yes? So a value is sufficiently small so that we would have a relatively precise approximation of the solution. Okay? So let's compute first y equals. Let's compute the median value equals high plus low divided by 2. Right? This would be the middle of the interval, the middle of the range. Yes? And then I can compute y as f applied to m. Okay? Because I don't want to compute it multiple times. Now, fm, we can have multiple situations, right? So what are those situations? So one is fm is already equal to 0. Yes? Another one is high minus low, I don't need the brackets, is less than epsilon. So in this case, we have already found the solution, right? M is the root, if this is true. Or if this is true, M is a very good approximation of the root. So we're going to say return M. M is the solution that we're after. Else if. This is how we write a sequenced test. So if this is true, okay, then do this. Else, let's see if something else is true. Well, if f low times f times y is less than 0, we are under the assumption that f low times f high is less than 0, right? So this is a precondition. Low is on one side of the axis and high is on the other side of the axis, right? So f low times f high is necessarily negative. This is a precondition, right? So now if f low times y is less than 0, yes, we're going to return what? Solve, same f, and f low, so low stays the same, but high is replaced by m. Yes? So if f low times y is less than 0, it means that this is on one side, this is on the other side of the axis. It means that there's a root in between. It means that the interval of interest is between low and m. Yes? So we're going to continue searching f between low and m. Else, the only thing that is possible here is only, so I'm going to write a comment just to remind you, f high times y is less than 0. This is the only thing that is possible. Now, this is a comment, is something that Python ignores. Whenever we start a line or we write this hash symbol, whatever follows after a hash symbol is any kind of text that will be ignored. It's a useful way for us to write notes in the program so that we can remember later what we were doing, We can write explanations of the solution. We can write reminders of any sort. Let's say I haven't handled all the cases. I come in later and say, remember to handle this case, and so on. So in this case, I'm going to return solve, f, and this time, the interval of interest is between m and high, right? So I'm going to have m and high here. All right? So this is the solve procedure. Is this clear? Yes?
Question, why do we need to say f low times y? Can it be just -1 times y? Like as a condition? If we just want to make sure that we're on the negative side of the axis?
What would that give you?
It's just checking y.
But you don't know that f low is negative.
Oh. Right. So the idea of putting f low times y is to make sure.
So, let's see how much we are. This one seems better. Right? So this is one possibility, right? So when I say between 0 and 100, and it happens that f low is negative, f high is positive.
Right.
The other possibility is this one, right? F low is positive, f high is negative. Right? What I know is that f low times f high is negative. I don't know whether this is negative and this is, I don't know which is negative and which is positive, right? Okay, more questions? Cool. So now we want to test. So we're going to say test our bisection method. So how would we test it, right? Well, we want to find whether the solution is correct or how close it is to a correct solution, right? So we're going to say print to x times x minus 3 equals 0 is, and we're going to say solve, and let me close this. How do I close this? Like this? Yes. Solve, and we were saying previously, right, if I want to encode x squared minus 3, I'm going to say lambda x times x minus 3. And I'm going to search between 0 and 100, as I was saying previously, right? And then, once we do this, we're going to print a verification line. Print for verification, right? SQRT3 equals, and let's see how much it is SQRT3, right? Obviously, Python is actually quite evolved and already has a function that computes SQRT3, right? So I'm going to say here SQRT3. Now, is this already accessible? All right, so in order to make this function available into the program, we have to import it. All right, why do we have to do this? Well, Python has a very large library with a lot of predefined things. We don't want to load them all in a program. We only want to load what we need. Right, so then we import things that we need from that library one by one. So we're going to say the library that we want is the mathematical library, math. And one thing we could do is say import math. You saw me doing that, right? And then once I have imported it, I can look inside math. And we can see what's there, right? So what is there? Well, we have the SQRT that we want to use. We have a function for sinus. We have a function for cosine. We have logarithm. We have factorial. We have all sorts of things. I think we did GCD at some point, right? So I think there's GCD somewhere. GCD here. There's Euler's gamma function used in statistics, and so on. So this is a relatively small library. There's everything that you need is already there. You just need to find the right library. Even the number pi, right? So I can see math.pi. We can see the value of it, right? And we can get a value for pi. Now, you see, every time I use this library, I have to say this math dot in front. I have to locate the library. So instead of doing that, we can actually say from math import SQRT. Once we do that, SQRT3 is available without the math prefix. I can write this and get the same result. So we're going to do exactly that. We're going to say from math import SQRT, and this will give us this function in our main program. Obviously, we don't want to do just a single test. Okay, so let's write more tests. I'm just going to copy and paste, and I'm going to say now x squared minus 2 equals 0, right? For verification, SQRT2. So we go here and say minus 2. 2. All right. What would be another interesting thing? For instance, we know that cosine, the cosine function, has a root between 0 and pi. Yes. So, which is actually what is pi divided by 2. It's exactly symmetric, right? So let's see how that works, right? So print solution to cos x equals 0. Solve. And interesting thing now, because this is a known function, I can say cos here. Now, in order to be able to use cos, I have to import here this one as well, cos. Right? And you know that it's pi divided by 2. I'm just going to go here and import pi as well. Right? So cos x equals 0 for verification, pi divided by 2. And I'm going to have pi divided by 2 here. Okay, so let's run this and see how well we're doing. So Python2, and we're going to say bisect. And we have invalid syntax there because it's missing a B, lambda. And of course here lambda. If I could just spell. Okay, so notice, solution to x squared minus 3 is 0. So this is the approximate solution that we found, right? And for verification, SQRT3 is this one, right? So notice that it has 6 decimal places identical. Obviously, if my epsilon was even smaller, I would have gotten more decimal places identical, right? How about square root of 2, right? So notice that it's identical up to here. So we get one extra. Oh, actually, we get quite a few of them. This is obviously by luck. So we get a lot more decimal places identical. It's just by luck, right? So we're imposing that about 6 decimal places be the same. Solution cos x equals 0 is, that's, because, why do we get that solution? So unfortunately, we have to restrict the interval to a single solution, right? If you think of cos, it's periodic and it has many solutions between 0 and 100. So I should have said here pi, right? Between 0 and pi, I want to find the solutions. And then I'm going to get pi divided by 2. Okay, so notice that this solution is 5707,963, right? So it's identical up to this point. So again, about 7 decimal places are identical. Yeah, is it clear? So you can, of course, use it for anything you like, just that how are you going to verify that it's correct? All right, so that's a problem, right? So that's why we chose relatively simple functions, so that we can easily verify the correctness of the solution. Okay, clear? Notice the fact that the argument to this procedure is a function. It's not a number, it's not a string, it's not a list, it's a function. Because of that, we say that solve is a higher order procedure. That make sense?
That first line, can you come back real quick up to the input line?
Okay, so next concept we want to talk about today is sequences. All right, so we discussed a little bit in the first class, but let's repeat all that. So there are several types of collections in Python, right? And some of these collections are sequences, meaning that it assumes that the elements are ordered in a specific order. We're going to discuss those. So one is the list. I'm going to say list equals, and I'm going to open a square bracket, and I'm going to say, I'm going to just take some random numbers separated by comma. All right, so this thing that is within the square brackets is a list. Open square bracket up to closed square bracket is a list. I think let's add a 7 here. The command line editor has tricked me. All right, so we assign that list to the variable L, and we can retrieve that value anytime we like. Okay, we can take any index any value of this from this list. So let's say I say L index 4, and I get the element of rank 4. Remember, the first element always has rank 0. So this has rank 0, 1, 2, 3, 4, and this is the fourth element, rank 4, right? So, and that's also the return value. We can select subsequences. So I can say L between 3 and 6. All right, so we get elements between ranks 3 inclusive and 6 exclusive. So this is the story with all ranges in computer science, in any programming language. The left is inclusive, the right is exclusive, right? So we go to the third rank 3, so this is 0, 1, 2, 3. This is rank 3. You can see it here, the same one. The same one is this one, rank 3, rank 4, rank 5, and it's exclusive. Rank 6 is not included. Yes, the number of elements in the subsequence is always right limit minus left limit. 6 minus 3 is 3. We get 3 elements. Okay? We can index starting from the right end of the list. All right, so I can say L index minus 2. So let's start with minus 1, right? Minus 1 is going to be the last element in the list. Minus 2, the last but 1. All right? Then I can use negative indices anytime I want, right? So if I want to say from 2 to minus 2, I'm going to get this, right? So this is element rank 2, and this is element rank minus 2. Starting from the right end, I will count 1 and 2, and the right limit of the range is exclusive. So this guy is not in the set, right? Everything before it is, right? So from 2, 3, 4, 5, and when I reach to minus 2, I stop and minus 2 is not included. Yeah? Now, we have this universal function called len that gives me the size of any collection. I can apply it to any aggregate. So if I say len L, I'm going to get 8, which is the number of elements inside, right? So whenever you see negative indices, imagine that there's a len inside. Because if I say L of len L minus 2, that's precisely the same thing, right? You see this guy here, right? The result is 3. You see this guy here. The result is 3, right? So always assume that when you see this minus 2, it's len L minus 2, right? It's a shortcut for that. So that's the correct way to compute it. We can also skip elements. So if I go here and I say, give me every second element, I'm going to get, starting at index 3, I'm going to get the third element, I'm going to skip the fourth, I'm going to get the fifth, and I'm going to reach the end of the interval. Right? So if I want to take every second, I'm going to take one, skip one, take one, skip one. If I want to have it take every third, I'm going to have take one, skip one, skip one, take one, skip one, skip one, and so on. Right? So I can skip elements if I want. I don't have to take every single element. Okay? Does it make sense? Let's define another list. And then let's see what's happening if I evaluate L plus L1. L plus L1 is going to be the concatenation of L and L1. L has remained the same, L1 has remained the same. This is a completely new list that does not share actually any elements. You see, it's the same elements, but I'm gonna tell you exactly what I mean by not sharing, what it means by sharing and not sharing, right? So let's say L2 is assigned L1 plus L2 plus L plus L1. All right. So L2 is completely separate. L and L1 have not changed their value. Now, with a list, I can change the contents of, so L2, let's print it again. With lists, I can change the contents of a list. So I can say that element index 3 be assigned 100. And now if I look at L, see that the element of rank 3 is 100. However, if I look at L2, the third element of L2 is still the old value, right? And in that, I'm saying that L2 doesn't share any elements with L and L1, right? L and L1 have been copied into separate copies, and then those copies have been used in creating L2, right? So whenever I change L1 or L2, L or L1, right, L2 doesn't change, even though L2 has been formed with L and L1. Okay, now we have ways of extending a list in a mutable way, right? So what you've seen here is creating a new list in an immutable way. Nothing that was there gets changed. We have created a completely new object. But I can say L is extended 2000, right? So now if I look at L, see that at the end we have the element 2000. All right, and then I can extend it with an entire list. I can say L.append, extend, sorry, L1. Now as I look at L, I can see that on top of the previous value, I have extended with a list. L1 has not changed, right, in any way. It's not that we have consumed the element of L1 to form L2, right? We made copies of those elements. All right, list comprehensions. Okay, so for instance, what if, before we talk about list comprehensions, what if I want to print all the values plus 1. So I have the list L1, right? And I want to print 11, 21, and 31. Well, a very simple way is for I in L1, and I put a colon here, right? So see how it goes, right? I take a variable and I make it scan through the elements of the list, right? So I will take turns in being 10, then later 20, then later 30. And we can say print I plus 1, right? So we see the values 11, 21, and 31. But something more interesting is to create the list that has 11, 21, and 31. How do we create that list? Well, I can use what we call list comprehensions. I say I plus 1 for I in L1. Okay? So this will give me those values aggregated inside a list. So let's make this L3. All right? This is similar to the notation you use for sets in high school, right? We used to say the set of all elements X such that, and we would give a property, right? So this is what we're doing here. We're making I scan through a certain range. Okay? Now, instead of L1, which is a fixed list, I can create a much larger list from a range. So I can say, for instance, I want the numbers from 1 to 100, right? So I can say the elements, all the elements I for I in range from 1 to 101. Remember, the right limit is exclusive. So then we have all the numbers between 1 and 100. How about I want all the numbers between 1 and 100 that are either multiples of 3 or multiples of 5? Well, I can add a filter. So I can say for I in range, if I %5 equals 0 or I %3 equal 0. Right? So now we have only elements that are either multiples of 3 or multiples of 5. And now you see the most general way of writing a list comprehension, right? So we provide a range and we provide a filtering condition. Yeah? So today in sequences we're going to play with this. That's what we want to do. Now, before we go to that, let's discuss a different kind of sequence, which we call a tuple, right? And you know what a tuple is from mathematics. 1, 2, 3 in round brackets is a tuple. It's not different, very different from a list, except that it cannot be changed. The list can be changed, right? I can say L1, 0 is assigned -1. Yeah? But if I say tuple 0 equals 1, 2, 3, and now I say tuple 0 sub 1 is 4, this doesn't work. It's an error, right? The tuple is immutable. There are significant advantages to that. All right. One being, we're going to see later that a tuple can be a key in a hash in a dictionary, whereas a list cannot. Okay. But for tuples, we have a similar comprehension, right? So instead of writing this with square brackets, I'm going to say tuple, and I'm going to use round brackets, and I'm going to get, instead of a list, I'm going to get a tuple. Notice the round bracket here and the round bracket here, right? Previously what we had was a square bracket here and a square bracket here, right? So we have a tuple comprehension as well as a list comprehension. Tuples can be added. So if I have 1, 2, 3, and I add it with 4, 5, 6, we get the longer tuple. However, we cannot extend or append to it, right? We cannot change the value of a tuple once it's there. Cool. So let's play with sequences. Most of what we're doing today in sequences can be done with either lists or tuples. Lists are typically more idiomatic in Python, so we're going to use lists, but we can easily change the programs to have tuples. All right, so the first thing that I would like to do is the sequence of powers of 2 up to some n, right? So I'm going to say def powers 2, right? And I'm going to have a limit here, right? So up to this limit, I want all the powers, and I'm going to return. All right. And remember, 2 to the power of 0 is 1, and 1 is also power of 2. So we're going to return 2 So the sign for power is ***, right? to the power of I for I in range of 0 and limit plus 1. Okay, so we verify that our result is correct. So we're going to say print powers of 2 up to, or sorry, the first 10 powers of 2 are, and we're going to say here powers 2 of 10. All right, so you see the result. We go up to 2 to the power of 10, which is 1024. Yeah. How about we want the Fibonacci numbers. Fib, we want the first n Fibonacci numbers, right? So how do we compute Fibonacci? Right, so we start from 0 and 1, or 1 and 1, depends how you, and we want every time, every next element to be the sum of the previous two, right? So we're going to write a helper. And so normally we start from 0 and 1, but I want to start from arbitrary numbers, A. So I'm going to have, I want to print n of them, A and B. All right. So if n is equal to 0, I'm going to return A. Yeah. Sorry, I'm going to return the empty list. Right? So if n is 0, I don't want any numbers. Else. All right. So I'm going to return. So the first element is always going to be A. Yes? Plus. So helper. And now there are n minus 1 numbers left, right? But if I want n minus 1 number, it's like I want a fresh sequence, but starting from B and A plus B. Does it make sense? Right? So we generalize. Normally, Fibonacci starts from 0 and 1. But we can start, say, I want to start from A and B, right? So the first number is A, the second is B, the third is A plus B, right? The fourth is 2A plus B, and so on and so forth, right? So now, if I have already put down A, it's as if I'm starting completely from scratch, but with the numbers B and A plus B. Yeah. And then I'm going to have helper of n, 0, and 1. If you like it better to start from 1 and 1, start from that. All right, so let's see the verification. Print the first 10 fib and we're going to say fib 10. So let's see how this one works. And notice that these are the correct Fibonacci numbers. Yeah. Is it clear? How about if I want the list of prime numbers? So let's say I want the primes that are less than n. So I don't want the first n primes. I want all the primes that are less than n. So I have to generalize again, right? What are the primes? What are primes now? Prime numbers. They're numbers that are divisible only with 1 and themselves. All right? So I'm going to define a helper, and I'm going to return the list of numbers that are greater or equal than k, less than n, and do not have divisors that are less than k. Right? So that's what I want to return here. So I want to return a list of numbers that are between k and n and do not have divisors less than k. If k becomes 2, the list returned is the list of prime numbers. Because they don't have divisors less than 2, except for 1, right? Therefore, they don't have any divisors, right? Because there's no numbers except for 1 less than 2. So they must be the list of, okay? So remember, this is what I want helper to return. Numbers between k and n that do not have divisors less than k. All right? So if k is greater than n, there's no number. So it's the empty list. Otherwise, we return, so the first number is going to be k. Yeah? Plus now helper k plus 1 and n is going to return because that's the definition, right? Numbers that are not divisible by anything less than k, right? So I'm going to, from these, I'm going to return the list of I for I in helper right? If I percent k not equal to 0, right? It's not divisible by k. So finally, I'm going to return helper between 2 and n. So we're going to say now print the list of primes less than 100 is, and we're going to have primes 100. Okay, and there you go, we have prime numbers less than 100. Does it make sense? Oops. We're defining a function. We can call it anything, right? It helps us compute the result. The name helper, because it's defined here and it's indented, is only valid inside the function. It's not valid outside. Because of that, there's no name clash here. I can reuse the name helper anytime I want, right? But it's a name I choose, right? I can call it H. As long as I use the name H everywhere, it's fine. Still works. And I can say F here. It's a name I pick. Doesn't matter. As long as I use it everywhere, right? See, everything still works correctly. Yeah. I'm going to change back. So usually we call this kind of functions helpers. Okay, last one. Towers of Hanoi. Let's try to find an animation. All right. So let's start with 3 disks, right? Have you seen this game before? Right? So we can only move. Sorry, I just want only 3 pegs. All right. So we can only move a disk on an empty peg or on a disk larger than it, right? And the objective is to move all the disks from here to, I think, here. Does it say exactly where those have to end? Okay, so I'm assuming the last one, right? So okay, so I moved one here, right? Then, and that's wrong. Let me restart. So I have to move all of them, all the 3 of them here, right? So I have to move this here. All right, I think I have to just click. Then I move this one here. Then I move this one here, right? Then I move this one here. Then I move this one here. Then I move this one here. Let me move this one here, right? And all right. So I would like to have a solution for any number of disks, right? How are we going to return the solution? The solution is a sequence of moves, right? And a move is a source peg and a destination peg, right? So it can be a pair, a tuple of two elements. A tuple of two elements, we also call it a pair. All right. So the result of our function should be a list of tuples, right? Each tuple being a pair of two numbers, the source peg and the destination peg for a single move. So how do we solve this? Well, we use recursion, right? And in using recursion, we have to start with a base case, right? So what's a suitable base case here? Most people would say, most beginners say, yeah, one disk. And that's not too bad. We can start with one disk. All right. So we move a disk from here to here. We're done. Finished, right? But the smarter base case is actually 0 disks. What do I have to do to solve the problem? Nothing. It's solved, right? 0 moves. Okay. Now, one important thing, right, which is generalization. We're going to see this repeatedly. So the problem that we are given is to move a stack of disks from the first peg number 1, to peg number 3. And then because these are fixed, it actually makes the problem harder to solve. We want to restate the problem. Let's find a solution of moving disks between any source and any destination, not just 1 and 3. Okay, how do we design a solution, a recursive solution? Well, I assume that the solution of size -1 is doing the right thing. Okay, so I'm going to put 2 here. And let's see, in case of 2, how we can take advantage of that, right? So I need to move 2 disks, all right? And obviously, in order to move 2 disks, I'm going to have, at some point, I'm going to have to move the largest disk from the source peg, which is 1, to the final destination peg, which is 3. And I'm going to say, well, but I already have the solution for size -1, which is 1, right? So I'm going to take n-1 disks, in this case 1, and I'm going to move them from 1 to 2. Not from 1 to 3, from 1 to 2. Once that has happened, I have freedom to move the largest disks from 1 to 3. And again, now I assume that the solution of size -1 is working. So I want to move n-1 disks, in this case 1, from 2 to 3. And done, right? Let's see, does it work for 3? Well, eventually I have to move the largest disk from 1 to 3, right? In order to move the largest disk from 1 to 3, I want to move all the smaller disks from 1 to 2. Yes? But in order to move all the, but now I have a smaller problem, right? Move only 2 disks. But in order to move all the smaller disks, I have to move the middle disk from 1 to 2. In order to move the middle disk from 1 to 2, I have to move all the smaller disks from 1 to 3. So I'm going to start with that. Move this from 1 to 3. Then I can move the middle disk here. Then I can move this from here to here, right? So now the initial size was 3, and I have solved the problem of size -1. I always assume that that works, right? I say, well, in order to move 3 disks from 1 to 3, let me move 2 disks from 1 to 2. Once I have done that, there's room to move this guy. And now, again, I have a solution of size -1. So let me move 2 disks from 2 to 3. Cool? Do you want to see it for 4? Let's do it quickly for 4. The number of moves is exponential, so each time takes twice more than before. So now I want to move 4 disks from 1 to 3. In order to move 4 disks from 1 to 3, I have to move 3 disks from 1 to 2. Once I have moved 3 disks from 1 to 2, the largest disk can move from 1 to 3. Yes? Then I have 3 disks here. I can move 3 disks from 2 to 3. Now, I need to move 3 disks from 2 to 3. I need to move 2 disks from 1 to 3. In order to move 2 disks from 1 to 3, I need to move 1 disk from 1 to 2. So I have solved the problem of size minus 1. Yes? I can move the largest disk now. And now again, I have to solve the problem of size minus 1, move from 2 to 3. So from 2 to 3 disks, I have to move the second disk from 2 to 1. Therefore, I'll have to move the first disk from 2 to 3. Easy, yes? So when I say move a disk from 1 to 2, I want to encode this as this, 1, 2. Right, so a sequence of moves is going to be something like 1, 2, 2, 3, 1, 3, right? So this is going to be something that looks like a solution, right? It's a list of tuples. It's a list of tuples. Every tuple represents a move. Okay? So we're going to print, and then we're going to verify that the result is correct. So let's do very quickly write def Hanoi of size n. And we were saying that we want to generalize. So typically the problem tells you to move from 1 to 3, but we're going to want to move from peg A to peg B using peg C as an intermediate peg. If n is 0, empty list, right? No moves. Else, all right, we return what? Hanoi, we want to move n minus 1 disks from peg A to peg C using B as an intermediate, right? Once we have done this, we can move 1 disk from peg A to peg B. And then my n minus 1 disks, smaller disks, are on peg C now. Yes? So I have to n minus 1. So from peg C, right, I have to move them to the, from peg C, I have to move them to the final destination, which is B, right? And what is left as an intermediary is A, right? So this is the solution. So let's print for size 4, and we're going to say Hanoi of size 4, 1, 3, 2. Okay, so let's run this and see the solution here, okay? So I'm going to bring the solution at the bottom of the screen. I'm going to reduce the size of the browser. So we have size 4, we have 4 disks. I'm going to restart, and let's follow and verify the fact that the solution is correct. So first I move from 1 to 2. then from 1 to 3, then from 2 to 3, then from 1 to 2, then from 3 to 1, then from 3 to 2, then from 1 to 2, then from 1 to 3, then from 2 to 3, then from 2 to 1, then from 3 to 1, then from 2 to 3, then from 1 to 2, then from 1 to 3, then from 2 to 3. And we're done, right? Yes? Clear? Questions? Code is here. So looking at how little code you need to write to solve a problem which appears relatively complicated, right? The power of this kind of reasoning is very high. It's a very powerful method of solving problems. Yeah, if there are no questions, thanks for coming. See you next time.